Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of the module Spur Gear and Design of Spur Gear. In our previous class of this Spur Gear and Design of Spur Gear, we started studying the bending stress in the spur gear tooth when force is transmitted from one gear to another gear. And in that we studied the Lewis bending equation and its limitation. So this lecture we will start with a brief review of the Lewis equation which we studied in our previous class, and thereafter the modifications in the Lewis bending equation. So the Lewis bending equation which we studied was considered a gear tooth with substituted to uniform strength beam like this, and we determined the bending stress by considering this as a cantilever beam subjected to a transmitted load Wt. The height of the beam was considered as h and the thickness at the root or at the support equal to T. So the cross-sectional area at the root was given by the width F, the width is this one, the width of the teeth, this, like this. So this was the width which is given by F, this is the width F, and the thickness is T. So the cross-sectional area which will be bearing the bending load is F multiplied by T. So considering this, the bending stress was 6 WTH divided by FT square. Now this equation was developed by applying certain simplifying assumptions, in which the first was the full load is applied at the tip of a single tooth. Therefore, there is no any sharing of the load. The second, the radial component WR is negligible. WR which acts on the gear tooth, this WR which acts radially, WR produces compressive stress along this cross section. Okay, along this cross section it produces compressive stress, and under fatigue compressive stresses are not detrimental. So neglecting WR will not make a phenomenal difference in the bending stress. The load is distributed uniformly across the full face width. So it was considered as the load which is transmitted, this Wt or the normal load W, is uniformly distributed all along the width of the tooth. Forces which are due to tooth sliding are negligible. Now we know that from the point of engagement A to the point of disengagement B, there is a combination of rolling and sliding when the tooth are under contact. But at the pitch point, when the contact point reaches at the pitch point P, then there is a pure rolling action. So in the derivation of Lewis bending equation, it was assumed that there is no sliding. It means condition at the pitch point or the contact at the pitch point was considered, because at other places along the path of contact, there will be a combination of sliding and rolling action. Stress concentration in the tooth fillet is negligible. In the derivation of Lewis equation, stress concentration at the fillet was not considered. That means the teeth, which was something like this, here, no, at the fillet, due to this fillet radius R, there will be stress concentration. But in the derivation of Lewis bending equation, the effect of stress concentration was not taken, because at the time of Lewis, it was not known. Now let us derive the equation, the Lewis equation, in the form that can be used easily in the design. Now at the point A, the bending stress derived was 6 Ft, the tangential force is Ft, or if this is taken as W, then it will be Wt, and this will be Wr. So this is the only difference in the nomenclature, which nomenclature you are using. So the bending stress mc divided by I is given by 6 Ft(h) divided by Bt square. Now let us draw a tangent on the fillet from the tip of the uniform strength parabolic beam shown by this dashed line. This is the tangent line, and from at A this line is tangent, and from A a perpendicular is dropped, and this perpendicular is intersecting the line of symmetry of the gear tooth at this point at a distance of x. This distance is x. This is x. This to this will be half of the thickness given by this to this will be t divided by 2, and this is x. Well, now taking the similar triangle, this similar triangle, okay, similar triangle, this with this length equal to x and this length equal to t divided by 2, and another triangle, this, this and this. So that triangle is this one, where this length is h, the height of the uniform strength beam, and this is again t divided by 2. Now these two triangles are similar triangles because this one of the length is same, and the angle is 90 degree, this angle is 90 degree. So from these two similar triangles, if I say it as a point A, this as a B, this as a small a, and this as a capital C. So the two triangles which were taken was triangle B small a C and triangle capital A and capital B and small a. Now from these two triangles we have t divided by 2 divided by x, t divided by 2 divided by x is equal to h divided by t by 2, h divided by t by 2, or t square divided by h, t square divided by h is equal to 4x. Now substituting equation 1 in equation 2, it gives sigma, that means t square by h is substituted as 4x. We have sigma is equal to 6 ft divided by 4 bx. So this will be 3, this will be 2. Now let capital this 2x divided by 3m is taken as a letter capital Y, which is called the Lewis form factor. Okay. So, let capital Y is 2x divided by 3m, where m is the module given by z divided by d, where z is the number of teeth in the gear and d is the pitch circle diameter. So, with this, the equation for bending stress becomes Ft divided by B, M and this Y and M. Well, so your Lewis bending stress equation is given by the transmitted load Wt divided by the tooth width, which is given here B, and Lewis form factor Y and the module M. So, bending equation is directly proportional to the transmitted load, inversely proportional to the tooth width and inversely proportional to the size of the gear, which is represented by module, and also inversely proportional to the Lewis form factor capital Y, or small y if in place of m the diametral module is taken. So, in our case it will be capital Y Lewis form factor, which is given by 3x divided by 3m, 2x divided by 3m, where x is this distance BC. Now, drawbacks of Lewis equation are the tooth load in practice is not static, because we have seen that when two pair of teeth will be in contact, a load Wt will be acting, but when the contact ceases, the load on the gear tooth will be 0. It means the load on the gear tooth is not constant, but it is varying like this. During this time there is no engagement, and so load on that particular gear tooth will be 0. Now, when contact started, there will be load throughout the contact period from small a to small b, and thereafter when at the time of disengagement and after disengagement, the load will become 0. It is dynamic, and so the load is not static, but it is dynamic, and it is influenced by the pitch line velocity v, which is given by pi d n divided by 60, where d is the pitch circle diameter, n is the RPM, and this will be given in mm per second, where when if d the pitch circle diameter is in mm. The next thing is the whole load is carried by single tooth is not correct. When the contact ratio Q will become equal to the circular pitch P, or when the contact ratio will be 1, then there will be no load sharing and single tooth will carry the complete load. But this is not the case. We keep contact ratio more than 1, and therefore there will be load sharing. So, normally load is shared by teeth since contact ratio is near to 1.5 or 1.2. The greatest force exerted at the tip of the tooth is not true, as the load is shared by teeth. It is exerted much below the tip when single pair contact occurs. We have seen that at the time of engagement at point small a, there will be load sharing. So, when the load is acting at the tip, then at that time there is load sharing. So, complete load is not acting at the tip. Now, from travel A to B, A is the start of point of contact and B is the end of contact, means the disengagement point. So, at A, when a load Wt is acting, it is shared by another gear tooth near point of disengagement B, because that pair of gear teeth have not yet engaged. it is at the verge of disengagement, but it is not disengaged, and so it will share the load. Now, at the point B, when a previous gear teeth will disengage, the normal load Wn has travelled some distance down to the tip of the gear. Therefore, at the start of engagement at point A, there will be sharing of the normal load Wn by a pair of another teeth at B. When the pair of gear teeth disengages at B, there will be no load sharing and the pair of teeth near A will carry the complete normal load Wn, but at that time the contact point has moved down, reducing the bending arm. So, maximum load will not come at will not act as the tip, but it will act slightly below the teeth. The next drawback was the stress concentration effect at the fillet was not considered. Later on, the AGMA modified the bending stress equation by considering all the factors which were not taken in the Lewis bending equation. Now, the Lewis factor can be determined from this table depending on number of teeth. If the number of teeth is 12, then the Lewis form factor capital Y is 0.245. If it is 28, then it is 0.353. Now, sigma, the bending stress, is given by Ft divided by Bym. So, with the increase in Lewis form factor, the bending stress decreases. So, here with the increase in number of teeth, the Y is increasing, and so the bending stress will decrease. So, you see, when you are moving in this direction, the Lewis form factor is increasing, and so the bending stress will decrease with the increase in number of teeth. And this data is particularly for a phi is equal to certain value, which is shown here. This is a table where Lewis form factor is given for pressure angle equal to 20 degree for the case of stubbed teeth, where addendum is 0.8 of the M. This is the full depth teeth with pressure angle equal to 20 degree, addendum is equal to standard module M, and dedendum is 1.25 M. So, for pressure angle equal to 25, these are the values. For pressure angle 25 degree and the dedendum is 1.3 times module M with large fillet. You can get the Lewis form factor from this. So, it is clear that Lewis form factor varies with form of the gear tooth, pressure angle and number of teeth. For a fixed value of number of teeth, for 20 degree pressure angle it was 0.2296 and for 25 degree it is 0.276, and so with the increase in pressure angle the bending stress is decreasing, will decrease in a gear tooth. This is a graphical way of determining the Lewis form factor. Knowing the number of teeth and knowing the pressure angle, you can find the Lewis form factor. Now, considering the different drawbacks of Lewis bending equation, AGMA, the American Gear Manufacturers Association, standard 2001 C95, developed a bending stress equation which is called the bending stress number as per AGMA. AGMA says the bending stress as the bending stress number. So, you can say it as a bending stress number or the bending stress, and that is given by the transmitted load W, the load which is transmitted by the gear tooth, that means this is the gear, the load which is to be transmitted Wt, the normal load is Wn, and the angle between these two is the pressure angle. Wt divided by F. F is the face width, means this face width of this face width, this length. F is the face width. Okay, and M is the module, and J is a new factor. In place of Y, the Lewis form factor, here we are using J, which is called the geometry factor. Well, this geometry factor has taken consideration of the stress concentration factor Kf and the load sharing. We will see in our coming slides. Ko is the overload factor for bending stress. That means the load is not static, and due to various reasons the Wt will increase by certain percentage depending on different factors, different applications. So, by including this overload factor, the overload effect is included in the bending equation. Now, this K size, we know that when we studied the design of the component under fatigue loading, then we found that the endurance limit SE obtained from rotating beam experiment was modified by a size factor. So, we had used the K size, and this SE dash obtained from rotating beam experiment was multiplied by K size to find the endurance limit of a component of a particular size, and that was due to the difference in size of the rotating beam specimen and our component. The same thing is done here. The size has an effect, and so the size factor is included to modify the transmitted load Wt. The load distribution or the mounting effect, one of the assumption the Lewis took was the load was considered to distributed uniformly all along the width. This is the gear tooth. All along the width, the load was considered to vary uniformly, but this not happens under actual loading condition or the actual working condition. Due to various defects, that may be the mounting factors, that may be called the mounting factor, the load may not be distributed throughout the width. It depends on the length of the width also. We will study in detail in our coming slides. Then Kb is the rim thickness factor. Sometimes the bigger gears are made in the form of rim. So, if the rim thickness is smaller, then there may be failure in the rim than the failure in the gear tooth. So, that effect we have to take into consideration. Now, Kv take consideration of the dynamic effect. The load was not, load which is acting on this gear is not static, but it is dynamic. It depends on the pitch line velocity and other factors. So, that should be taken into account, and that is taken account by this dynamic factor or the velocity factor. This is also called the velocity factor. Velocity factor or the dynamic factor. This Km, the load distribution factor or the mounting factor. Well, so the bending stress which will develop at the root as per AGMA is given by Wt divided by Fmj, Ko, Ks, Km, Kb and Kv. Now, issues which are included in the AGMA bending equation are transmitted load magnitude, the effect of overload, dynamic augmentation of transmitted load, size, geometry, that means the pitch and the face width, distribution of load across the teeth, rim support of the tooth, Lewis form factor and root fillet stress concentration. Now, the effect of stress concentration was considered by taking stress concentration factor Kf is equal to H plus small t divided by small r to the power capital L multiplied by within the bracket small t divided by small l to the power capital M, where capital H is given by 0.34 minus 0.458366 multiplied by 2 phi, and capital L is given by this formula, capital M is given by this formula, and thus the value of R, the fillet rate, this R in this equation, this is taken with respect to the fillet radius R, F, R, F. So, R in this equation is given by B minus RF, B is the width divided by D pitch circle diameter divided by 2 plus B minus RF. So, knowing this R, knowing the pressure angle F, knowing the thickness of the tooth, this at the fillet, this one, this is the T, knowing the L, this height of the gear tooth, this L, from small a to the vector Wt, the transmitted load, and small a is the point where a line is drawn from the point of application of Wt tangent on this fillet. So, this A is the point where this line is tangent on the fillet. So, thickness T, L. So, from that we got the value of H, L, M, R. Substituting them, we get the value of Kf. So, the B in this equation, this one is the dedendum. Dedendum means this is the pitch circle, and the root circle is suppose somewhere here. Dedendum circle or the root circle? Well, so this is your dedendum given by small b, and D is the pitch circle diameter or the pitch diameter simply. So, this Kf was found from this, the AGMA geometry factor J employs a modified value of the Lewis form factor. This Y is not the Lewis form factor which we studied, it is a modified value of Lewis form factor, and this is based on the single point, highest point of single tooth contact. Well, so it is also denoted by Y dash. Y or Y dash you may say, a fatigue stress concentration factor as we discussed just now, and a tooth load shearing magnitude Mn. So, with this J is given by, in terms of Y dash, the modified Lewis form factor Y dash, the stress concentration factor Kf, and the load shearing ratio Mn. So, geometry factor J, which is used in the AGMA bending stress equation, is given by Y dash divided by Kf Mn. Y dash in the above equation is not the Lewis form factor, but it is modified Lewis form factor. The value of Y here is obtained from the calculations within AGMA 908 B89 and is often based on the highest point of single tooth contact, the point where single tooth contact will occur. Because we are saying that due to load shear, single tooth contact will not occur at the tip, but it will occur slightly below the tip. So this is the highest point of single tooth contact. When there is load shearing, when there is load shearing. Now when there is no load shearing, then this is the point where maximum load occurs, but under load shearing condition it occurs slightly below, and so the bending stress will be lesser. The factor Kf in the equation of geometry factor is called the stress concentration factor by AGMA. It is based on a formula deduced from a photoelastic investigation of the stress concentration in gear teeth over 50 years ago. The load shearing ratio Mn is equal to the face width divided by the minimum total length of the line of contact. For the case of a spur gear, the Mn is equal to 1. Now, we have a figure or we have a graph from where we can find the geometry factor J, knowing the number of teeth for which geometry factor is desired. So let you want to find geometry factor for the pinion, then on this side you will take the number of teeth on the pinion. Now if you want to determine geometry factor for the gear, then on this side you will select a point corresponding to number of teeth on the gear. Now you have different curves. So if you look after these curves, then number of teeth in mating gear is written. It means if you want to determine J for pinion, then number of teeth on the pinion will be taken on the x-axis, and you will select a curve corresponding to number of teeth on the gear. So let number of teeth on the pinion is 20 and number of teeth on the gear is 85. Then you will select this curve to determine the geometry factor J. Now if there is no load shearing, load applied at the tip of tooth, then there is only one curve corresponding to all mating gears number of teeth. Well, and this is for load applied at highest point of single tooth contact, when the load was acting slightly below the point where maximum load was acting at the tip. Now the overload factor. The overload factor considers the probability that load variations, vibrations, shock, speed changes and other application specific conditions may result in peak loads greater than the transmitted load Wt being applied to the gear tooth during operation. That means due to various factors, those factors may be the load variation, vibrations, shock, speed change and other application specific conditions, the load which is acting on the gear tooth is more than Wt. So that more than is taken account by this overload. So the actual load which is acting on the gear tooth will be equal to Wt multiplied by the Ko. Now many industries have established suitable values based on experience. Like this table has along the first column the source of power. The source of power first is uniform, then light shock and medium shock. That means in the driving gear is connected to a source of power which is uniformly supplying the power, or it is supplying power with light shock, or it is supplying power with medium shock. Then according to the type of source of power, you will select a row. Then driven machinery. Driven machinery means the driven gear will drive certain machinery. So this shows that machinery. If the nature of the machinery is uniform, then you will go for this column. If it is moderate shock, then you will go for this. If it is heavy shock, then you will go for this. Now let's see which applications will come under uniform, moderate shock, light shock, or the medium shock, heavy shock. For power sources, we will use the following. Uniform electric motor or constant speed gas turbine will be called uniform source of power. Examples: continuous duty generator. Light shock water turbine, variable speed drive. Examples: fans and low speed centrifugal pumps. Liquid agitators, variable duty generators, uniformly loaded conveyors, rotating positive displacement pumps. The moderate shock, the multi-cylinder engine. If the engine is the multi-cylinder engine, then it will be under moderate shock category. Now examples: high speed centrifugal pumps, reciprocating pumps, compressors, heavy duty conveyors, machine tool drives, concrete mixers, textile machinery, meat grinding saws. Then heavy shock, rock crushers, punch press drives, pulverizers, processing mills, tumbling barrels, wood chippers, vibrating screens, railroad car dumpers. These all will come under heavy shock category. So knowing the source of power and the driven machinery, we will have a certain value of cell value. So suppose the source of power is uniform. That means you are getting power from the motor and you are distributing it to the uniform type of driven machinery. Then the cell value or the KO is 1. It means the actual load which will be acting on the gear will equal to WT multiplied by 1. It means W is equal to WT. But if the source of power is uniform but driven machinery is of moderate shock, then it is 1.25. That means the actual load will be 25% more than the transmitted load WT. WT multiplied by 1.25. So like that, for heavy shock, 75% increase in the actual load on the gear tooth. Now the size factor Ks, which was used in the AGMA bending stress equation or the bending stress number. The size factor reflects non-uniformity of material properties due to size, because we say that with the increase in size, there is more possibility of defects in the material, and so the strength of the material will be lesser. This is the reason why the nanoparticles have very high strength, because their size is very, very small and the chances of defect is rare, and so it will have very high strength. So this thing is taken account by Ks, and also the non-uniform distribution of properties. If properties are not same throughout the volume of the material, then also there will be the indifferent strength. Now it depends on tooth size, that means the module, diameter of part, ratio of tooth size to diameter of part, face width, area of stress pattern, ratio of case depth to tooth size, hardenability and heat treatment. Now similar to the way we determined the size factor for non-circular and non-rotating shaft. We can find the K size for gear also. What we will do is, we will take this teeth, this particular tooth is taken, one of the tooth with module M, and the height from small a to the line of action of WT equal to L. Then this L will be equal to the addendum, this addendum, and the dedendum, A plus B. Standard addendum is equal to 1 module and standard dedendum is equal to 1.25 module. And so L may be given as 2.25 m. Now, from Lewis equation, when we derive the Lewis bending equation, then this T thickness of the gear tooth along the fillet, this T was found in terms of this length L and this X, just to remember it, this X, and the equation was this T is equal to under root 4LX, where X is given by 3ym divided by 2, where y is the Lewis form factor, m is the module. So, knowing this and this, now we can find the equivalent diameter DE of the rectangular section in the bending. That means this under this section or at this section, the cross section is given by T, the thickness, and width. Width is large. Width is given by F, width of the gear tooth in this direction. That means this. So, this is F. Okay. This one is the top land, as we studied, this is top land. So, rectangular section with F and T, and this is under bending. Well, so the D equivalent is equal to 0.808 under root FT. This equation is the equation which was found by comparing the 95% or more than 95% of the maximum stress, and which acts on which section. That means, let we have a rectangular section, and on this rectangular section, if a bending stress is acting or the bending moment is acting, and so the bending stress distribution will be something like this. Well, now the volume or the cross section which is subjected to stresses either equal to or more than 95% of the maximum stress. That means, here the maximum stress is acting sigma maximum. So, at this point, let the stress is 0.95 of the sigma maximum. Well, so this area is calculated. This is the area which is subjected to stresses equal to or more than 95% of the maximum stress, and this also. This is for the case where the cantilever beam, this cantilever beam is subjected to this type of load. Well, now this area was compared with the rotating beam, means circular cross section subject to rotating bending. Now, when it is subjected to rotating bending, then the bending stress, which is either equal to or more than 95% of the maximum stress, will be this annular ring, this one. Now, if length of the beam of this cross section is same, then this area which is subjected to bending stress equal to or more than 95% of the maximum stress, and this is compared. We find the equivalent diameter. So, for the case of bending, the equivalent diameter equation is 0.808 under root Ft, where F is this one, T is this one. Now, this D equivalent is used in the case size for the endurance limit modifying factor. This case size is the, if SE dash is the endurance limit obtained from the rotating beam experiment, and SE is the endurance limit of our component of a size different than the rotating beam experiment, then we get this SE is equal to SE dash multiplied by K size. This is called the Martin factor. So, the K size is taken from that concept. So, K size is given by D equivalent divided by 7.62 to the power minus 0.107. Now, this is valid when D equivalent is greater than or equal to 2.79 and it is less than or equal to 51 mm. And if it is greater than 51 mm but less than or equal to 254 mm, then this is the formula. Now, this K size will be less than 1. Well, now our size factor for the gear is more than 1, because due to size effect we want to increase the value of Wt by multiplying with the K size. So, Ks is equal to 1 upon this K size, small K size. This is K size. Okay. So, substituting these values in this equation, F and T with this and this one, T from this one, X from this, we get Ks is equal to 0.904 within the bracket Fm under root Y to the power 0.0535. So, this equation may be used to determine the K size of the AGMAs. Now, next is the load distribution factor. In the Lewis form factor, it was assumed that load is uniformly distributed along the width. Along the width, load is uniformly distributed, but this not happens due to various reasons. So, that we have to take into account. The determination of load distribution factor is based on many variables in the design of the gear themselves, as well as in the shafts, bearings, housings and the structure in which the gear drive is installed. Because if the shaft is not accurately mounted, shaft of the driving gear and the shaft of the driven gear are not accurately mounted, then due to that, when the load will be transmitted from one gear to another gear, it will not be uniform throughout the width. Now, if width is very long, then also there may be a chance that the load will not be uniformly distributed. So, various factors are responsible for non-uniform distribution of load along the width. So, therefore, it is one of the most difficult factors to specify. Much analytical and experimental works is continuing on the determination of value of the Km. Now, this table gives us some value of Kf, this Km for different support conditions and others. Like the first row says characteristic of support. So what type of support is? So there are 3 conditions, and the face width. If face width is 0 to 50, then these are the values. If it is 150, then this one, 225, then this, 400 and up to this one. So let's take first support condition, the bearings which are used to give the support of the shaft and the finish and others of the gear. So let's see here the accurate mounting. That means mounting is very accurate, there is no any misalignment, and the gear which is mounted here should be mounted in such a way that at the point of mounting of the gear there is no deflection in the shaft, because when there will be appreciable deflection, then also there will be a chance of non-uniform distribution of load along the width. Okay. So next thing is small bearing. Small bearing clearances are there, minimum deflection is there, and the precision gears. That means gear is manufactured or made with high precision. So if the precision is high, minimum deflection is there, and the small bearing clearances are there, and accurate mounting is there, then with face width up to 50 mm, it is 1.3. That means W will be equal to WT multiplied by 1.3. That means 30% increase in WT. We are increasing WT by 30%, and so sigma, which is directly proportional to WT, will increase by also 30%. So we are presuming that more stresses are developing at the root of the gear. Now the next is less rigid mounting. The mounting is less rigid, and so there may be a chance of misalignment, less accurate gears, contact across the full face. Then the values are 1.6, 1.7, 1.8, 2.2. You see, when you are moving in this direction with the increase in face width, the amount by which your WT will be increased is increasing. Here 60%, 70%, 80% and 120%. Then last one is accuracy and mount. So you see, these factors are taken very big, 2.2, 2.2, 2.2 and 2.2. So knowing the condition, you can select the mounting factor Km, and that may be used to get the bending stress. Now if the intensity of loading on all parts of all teeth in contact at any given time were uniform, the value of Km would be 1. But this is seldom the case. Following factors can cause misalignment of the teeth on the pinion relative to those on the gear. First, inaccurate gear teeth, misalignment of the axes of shafts carrying gears, elastic deformations of the gear, shaft, bearings, housing and support structures, clearances between the shafts and the gears, the shafts and the bearings and the housing, thermal distortions due to operation, crowning or end relief of gear tooth. So due to any reason, if there is no any uniform distribution of load, we have to take into account by multiplying the transmitted load WT by the Km, the mounting factor or the load distribution factor. The designer can minimize the load distribution factor by specifying the following: accurate teeth, a high quality number, narrow face width. We have seen that with the increase in face width, the mounting factor was increasing. So if the face width is smaller or narrower, then we can minimize the load distribution factor. Gears centered between bearings. That means if the gear is the shaft is supported like this, and the gear is in between, like a simply supported beam loaded in the mid. Then there is lesser chance of misalignment or non-uniform distribution. Short shaft span. So in comparison to this simply supported, suppose the shaft is a cantilever type, then there will be more deflection. Short shaft spans between bearings, large shaft diameters, high stiffness, rigid stiff housings, high precision and small clearance on all drive components. The next one is the rim thickness factor. When the rim thickness is not sufficient to provide full support for the tooth root, the location of the bending fatigue failure may be through the gear rim rather than the tooth fillet. In such cases, the use of a stress modifying factor Kb or Tr is recommended. This factor, the rim thickness factor Kb, adjusts the estimated bending stress for the thin rimmed gear. It is a function of the backup ratio Mb, which is given by Tr divided by Ht, where Tr is the rim thickness and Ht is the full depth of the gear tooth. Then Kb, the rim thickness factor, is given by 1.6 log of the 2.243 divided by Mb. If Mb is less than 1.2 and it is equal to 1 when Mb is greater than or equal to 1.2. This Kb may also be obtained from this graph. Knowing the backup ratio Mb, you can get the rim thickness factor. The next one is the dynamic factor Kv, which we will study in our next class. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that's the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life. You are looking at things from a physical point of view. You are looking at the corresponding changes inside the body. You are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are a whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.